Welcome back once again as we continue our discussion on applying machine learning to different types of materials science problems. We have already started with this problem of predicting the crystal structures in case of high entropy alloy. Of course, this is a fairly simple-minded problem, and so we sort of already limit ourselves by saying that we will predict only the face-centered cubic type of crystal structure, the body-centered cubic type of crystal structure for the solid solutions, and then we have been treating all of the intermetallics as a single class of crystal structures. So with that, let us continue. Let us pick up from where we stopped. We had discussed about how the data set would be prepared, and in case of the preparation of the data set, we broadly said that you need to have some amount of elemental descriptors, which are the composition based feature vectors, and then you also need to have some of this calculated features. So let us actually dive into this and see what features are we actually using for this particular model. So in case of the elemental features, this composition based feature vector type of calculations, we are looking at features which are asymmetric. So for instance, you have got the molar volume asymmetry, you've got a metallic radius asymmetry, you've got a covalent radius asymmetry, the asymmetry in cohesive energy, bulk modulus, and so on. So why bulk modulus? Because since we are talking about high entropy alloys which tend to form solid solution, the elastic contribution to the strain energy becomes important, and therefore the bulk modulus also becomes important. So in addition to this asymmetry features, we also have other composition based features. One of them happens to be this average melting point. We also have things like the valence electron concentration. We also have things like the Allen electronegativity, the density of the alloy, and so on. So we have this asymmetry based features. We also have this composition based feature vectors, and as we talked about, we also have the thermodynamic potential, which are the vectors or the features that are actually being computed using physical principles. So here you will have a bunch of contributions to the enthalpy of the material, and then you also have got the configurational entropy. So these are our features, and if you think about it, these features capture a variety of things. We have already very briefly discussed the Hume-Rothery rules of solid solution formation. And according to the Hume-Rothery rules of solid solution formation, there has to be a maximum limit of size misfit for a substitutional solid solution to form. Now, with the exception of small atoms like lithium, in most of the cases, the atomic radii are not that far off from each other, not so drastically different that you will end up having interstitial solid solution. So we'll be looking mainly at the substitutional solid solution. And therefore, the asymmetry in the radii becomes very important. We also know that for single phase solid solution to form, the electronegativities should be fairly similar, and therefore looking at these things like electronegativity, looking at the valence electron concentration, which decides which type of structure will be formed, whether a BCC will form or a FCC will form, those things starts becoming important. And eventually we will also need to consider the interaction between the different atoms, because after all, we are also considering the formation of intermetallics where the interactions are going to be fairly strong. And so that is really where the chemical contribution to the formation enthalpy is coming in. And of course, when we are looking at the chemical contribution to the formation enthalpy, if you remember our discussion on Miedema's model, you will remember that there was a gamma parameter, and this gamma parameter was 0 for solid solution, this was 5 for liquids, and this was 8 for the intermetallics. So when we are computing the formation enthalpies, we actually need to compute the formation enthalpies for the intermetallics. We need to compute the formation enthalpies for the solid solutions as well. Alright, so with this set of features, we will then go ahead and train our model. So this is basically how we have set up our problem. Just to recap a little bit, we have made our high entropy alloy database. To that, we have added a bunch of features. These are both the composition based features as well as the physically calculated features. And then after that, we will proceed to our actual machine learning model. So in this particular case, artificial neural network was used. And so in case of an artificial neural network, you will have an input layer, and when we are giving the input, we are starting with the composition, and along with the composition, the different features are getting populated as well. After the input, you've got a bunch of hidden layers. This is really where the fitting part is occurring in case of the neural networks, as you've already discussed in some of the earlier lectures of this course. And this hidden layers can have different number of nodes. You can have different number of hidden layers. So the number of neurons you have got in each layer and the number of hidden layers themselves, those are things which we can classify as hyperparameters. So if you look at all of the other parameters like the biases and weights for the neural networks, those are things which the model actually has to get trained with and learn. So those are things which the neural network itself is sort of optimizing, but hyperparameters are the terms that you have to actually optimize. So you get to specify how many hidden layers you'll work with, how many neurons will be there in each of the hidden layers, and so on. Now, as far as the output is concerned, in this case, our output would be whether there is a FCC present, whether there is a BCC present, and whether there is a intermetallic present. Now, what happens if you have significant probability of a FCC being present and a significant probability of a BCC being present? It basically means that you will have a combination of FCC crystal structure and the BCC crystal structure in this particular type of alloy. So this is basically what we call a multi-level classification. This is not a single level classification. I'm not setting up the problem saying that only one specific crystal structure can exist. I'm simply computing what is the probability that any one structure can exist regardless of what other crystal structures are present. So that's why this is a multi-level classification type of problem. And then we wanted to take this thing a little bit further. So what we have also tried to do is we have tried to quantify how much of each feature will be forming. So this is a little bit more advanced type of problem. I'm not going to discuss this part too much, but for most part we are going to stick with this multi-level classification for rest of this lecture. Now, this model has to be trained, and when I say that the model has to be trained, it means that this neural network will need to have an input layer, and this input layer has the 14 features that we have already discussed. And then after that, what we have done is we have got a very deep neural network where you have got multiple hidden layers, and as you go from one layer to the next, the number of neurons is progressively getting decreased. So in this particular case, our number of neurons or number of nodes in each of the hidden layer varied between 10 and 40. So it's 10 in the last layer, 40 in the first layer, and we had a total of 7 hidden layers. So you can see that this is a very, very deep neural network. And normally I would not really recommend that we use very deep neural network right at the outset. Sometimes if it may be necessary to increase the depth of the neural network in order to fit your data properly. So in this case, we had a very deep neural network. Now, one of the challenges when you have really deep neural network is you can very easily end up with overfitting. So you have to take measures to avoid this overfitting challenges, and there were a number of things that can be done and that we did in this particular model, and one of them is to actually take a ensemble averaging type of approach. So what do I mean by ensemble averaging? It means that what I have done is I have sampled different parts of the data set, and I have made a large number of models. So we made lots and lots of neural network models. About 150 different ANN models were made with the same data set, sampling the data set differently. And after you make this large number of models, what you basically do is you average the predicted value over all of this neural networks. So by taking this type of averaging over many neural networks, over an ensemble of neural networks, that is going to help mitigate the challenges associated with this really deep neural networks with not that many number of data points to some extent. That is, of course, not sufficient. There are other things that we have done, and we are going to talk about it shortly, but this is one of the ways that we do. So after you have your hidden layers, you will be having an output layer, and in this output layer, we are basically getting a probability value of whether a FCC will exist or a BCC will exist or an intermetallic will exist. And so how do we get the probability? We use a softmax function. So as you might be remembering from the earlier lectures, the softmax function goes something like this, and it is basically scaled between 0 and 1. So it's really giving you the probability. Now remember, it is not necessary that the alloys we are looking at is single phase. And therefore, the sum of probabilities in this case, in a very counterintuitive manner, is not necessarily equal to 1. You could have a very high probability of a FCC being present. You could have a very high probability of a BCC being present if you are having a FCC plus BCC type of structure for that particular high entropy alloy. So in that case, you might actually have the sum of the probability of FCC and sum of the probability of BCC being more than 1. What really matters is that individually the FCC probability should lie between 0 and 1. Individually the BCC probability should lie between 0 and 1. And individually the intermetallic probability should lie between 0 and 1. So by using this softmax type of function in our output layer, we are ensuring that we are getting a proper probability. And based on the probability, if the probability is less than 0.5, which is actually an arbitrary cutoff, but maybe a fairly reasonable cutoff, we are starting to predict whether the alloy is going to have a FCC type of structure, or it has any BCC type of structure, or whether it has any intermetallics which are forming. Now, anytime you use models like this, it is essential that you cross-validate. So we did 5-fold cross-validation, and once you do the cross-validation, you want to actually represent your entire output that you are getting from the cross-validation properly. And so for that, we have something which looks like this matrix over here. We call this the confusion matrix. So basically what we are doing in the confusion matrix is we are simply noting that in our actual data set that we have used for training, how many of each of these labels were present. So in this case, what we say is we have in actual the FCC being present 35 times, and the model also predicted it 35 times correctly. There were other situations where the FCC was actually existing in the database, but the model predicted it incorrectly. Of course, the models are not going to be 100% accurate, right? So essentially what you are doing is you are simply noting down the number of cases where the predictions were actually perfect, and then you are also noting down the number of cases where the predictions were not really that great. So for instance, if I have a situation which says that the BCC is occurring just by itself 2 times, but in actually what's happening is I am observing a FCC plus intermetallic. So those type of things have to be noted. And based on that, what we get is a couple of things called the precision and the recall. So you want to look at the precision and the recall, and you want to check the percentage of your precision and recall in each of these cases, and you want to ensure that the percentages are fairly high, because that gives you an idea that your model is actually working in a reasonable amount of manner. Now, of course, after we train the model, we don't simply say that whatever we have trained is fine. We actually need to test it. So over and above the data set that was used for training the model, we now created a new data set comprising of about 58 alloys, which we called our testing data set. So the model was not trained with any of the alloys in this new 58 alloy data set. And then we tried to do the prediction for this 58 alloy data set, and then we tried to see how accurate our predictions was. And it turned out, if you remember in the previous video, I showed you some number, like in some cases the prediction was 90% accurate, in some cases were 86% accurate, and so on. So the numbers showed in the previous video and the table of the previous video about the accuracy of the present model, those were the numbers which were based off this new 58 alloy data set. Once you have a model like this, where the composition is your sole input, you can actually use this model to explore lots of new compositions which have not yet been made. So for instance, here we are taking the example of a aluminum, titanium, chromium, iron, nickel quinary alloy, and we actually took the experimental data from the literature, and it so happened that those who did the experiment kept the chromium iron nickel ratio constant, and then they varied the amount of titanium and aluminum, and therefore we depicted this using a pseudo ternary diagram like this, where on one side you had 100% of chromium iron nickel, meaning chromium 33, iron 33, nickel 33. On one side you had pure titanium, and on one side you had pure aluminum. And then we did the predictions with all the compositions that were tested experimentally. So most of the compositions that were tested was from this corner of the phase diagram, and that is basically what we are showing over here. You had a pure ternary compositions, then you had some couple of quaternary compositions, and then there were a couple of actual quinary compositions. So what we did was we predicted the probability that a FCC phase will be present, and you can see that in this color bar 0 correlates to a 0 probability. This blue correlates to a 0 probability of FCC being present, and 1 correlates, which is this red color, correlates to the probability that FCC is absolutely going to be present. So what you can see is on this corner of this diagram you have a very high chance of FCC being present, and as you move away from it, the chances of a FCC based solid solution goes down. Similarly, we did the same type of plot for BCC, and we did the same type of plot for the intermetallic. And by doing that, we now start seeing that in this particular corner, we should not really be having a BCC type of solid solution. And if you look at this very corner part clearly, it also tells you that we should not be having this intermetallic type of structures. Now, we did not just do machine learning calculations. We actually validated our machine learning calculations not just with the experiments, but by a series of first principle calculation, DFT based calculations. Now that's another story, and I won't go very deep into it, but essentially what happens is, using your density functional theory type of calculation, you can actually start predicting or calculating the formation enthalpy, and then with that you can start making guesses as to whether the crystal structure is stable or not. So the DFT part is not something that I want to discuss over here, which is why I have not put it, but the figure you see over here is really a comparison of the experimental results and our machine learning prediction. So as you see, the experimental result says that the phase fraction of the face-centered cubic solid solution decreases as you are increasing the amount of aluminum. So as you can see from this figure over here, as I'm increasing the aluminum, I'm going from the red region to the blue region, which means that the probability of FCC is going rapidly to 0. And then, of course, when I'm looking at the higher aluminum concentration, which is this over here, again, you will see that there is some finite probability of a face-centered cubic solid solution being present, and therefore you can see that this is increasing. The same thing can be done for the BCC and intermetallic type of condition. And so this is a way in which once you have developed your model, you can actually use the model to explore your material system even more. So just summarize what we discussed. We adopted this process in which we started by curating the high entropy alloy database. Then we calculated the alloy features. After that, we implemented an artificial neural network. Not just a single artificial neural network, rather an ensemble of artificial neural networks. And our predictions were basically the average of this ensemble-based artificial neural networks. So few things, takeaway points I would want to emphasize. The first thing is you should know your database well. Many of the model limitations can be identified simply by exploring your database and knowing the limits of your database. The next thing that's really important is you should cross-validate. The cross-validation part is really important. You do a 5-fold cross-validation, 10-fold cross-validation. That really depends on how much data you have got and it's always good to cross-validate extensively so that you can figure out that if there are certain weird conditions under which the models is actually not performing well. In addition to cross-validating, you should also tune the hyperparameters of your model sensibly. Try not to go very deep despite what we did. I think it's always a good idea if you can do the fitting with a relatively shallow neural network, because that way the chances of overfitting is going to be less. And if you do have to go to relatively deep neural networks, it's always a good idea if you can average over ensemble instead of simply relying on a single model, especially because in materials informatics, in most of the cases, the size of your database is fairly small. And finally, you also need to think how you can slice and dice your data so that you can get more and more insights from the model. So here in the previous case, when we were talking about this aluminum, titanium, chromium, iron, nickel, we simply compared with the experimental data. We visualized our model predictions by using this contour type of mapping, and that allowed us to sort of visualize where the face-centered cubic crystal structure would be disappearing, where the body-centered cubic crystal structure would be appearing, and so on. So simply by running your model over a variety of parametric values, you can get an idea of how the model is going to behave and what the model is going to predict. So that is the first level of slicing and dicing the data that you can generate with your machine learning model. Beyond this, of course, there are other methods by which we can sort of interrogate our model and get an idea as to what the underlying physics is getting captured by this machine learning model. So those are the topics that we will be discussing in the upcoming lectures. So with that, I hope you now have a good feel for what you can really do by applying machine learning to material science after having gone over this entire example over this lecture. Thank you for joining, and thank you for listening to this lecture. Hope to see you once again next time.